All right, so today we're working on rotational kinematics. In order to do that, though, we need to start by talking about some new definitions. And the first one is something you're familiar with in calculus and analysis and trig, and that is a radian. So let's go and define that really quickly. If you're given a circle with a radius r, and you travel along the edge of the circle, the arc length s, exactly one radius, you get a radian. Okay. Now you can mark it as the arc length s, or of course you can mark it as the angle theta, but either way you have traveled one radian. Okay. So again, one radian, which we're going to simplify from this point on as just a rad, is defined as the distance around a circle circle equal to one radius, or rad. All right. Now, because of that, we're going to be left with some interesting points. The first one is we have a bunch of different types of measurements we can use when we call it. So let's talk about it. So in degrees, one full rotation, and this is how we're going to use our conversion factor, of course, is 360 degrees, though we'll very rarely use that. We know that 360 degrees is exactly one revolution, and we know that because my distance around a circle is 2 pi r, that my radians would just be 2 pi radians. Okay. And then the actual arc length, the actual length s, would be 2 pi r meters. Okay. So make sure we got the units here. We're at 360 degrees, 1 revolution, 2 pi radians, and 2 pi r meters. And this will allow me to use a little bit of dimensional analysis to convert back and forth. So if I told you 2 revolutions, you know we're traveling 4 pi rad. If I tell you 7 revolutions, I know I'm 14 pi rad. So that just gives you an idea, or radians. I don't know why I'm saying rad, I'm being annoying. But nonetheless, now, this conversion leads us to one of the most important relationships, and that is the change in arc length, or the change around the circle, the actual tangential distance traveled. Distance traveled is going to equal your radian value, or your change in radian value, which we're going to call angular displacement, change in theta, times the actual radius of the circle. So we have a couple new terms then. We have angular displacement, which is best measured in radians, and is how far around the circle you've gone, how much you've rotated, if you want to think of it that way. If I've rotated 2 pi radians, then I have rotated 1 full time around the circle. Now be careful, sometimes I want actual distances, and when I want to know an actual distance traveled around the circle, I simply have to multiply my angular displacement by my radians. So now that I have the base definition, I can go on to speed and velocity. Actually, I really should say this is velocity because direction will matter eventually. But for now, it's still speed. So what is my definition of angular speed? Well, the first thing is we're going to use a new symbol. That is actually a lowercase omega. So that is my angular velocity. And it's simply going to be defined by a change in displacement, angular displacement, with respect to time. Of course, this is my average. If you take down and do instantaneous, you're taking the limit as delta t goes to 0. So what would my units be for angular velocity? Well, it's a radian on top, and it is seconds on bottom. So there is a couple conversions we want to know. The first one is rotations per minute, or rotations per second. We like to use this term. You hear it with cars. So let's do a real quick example. So if I had 1 rotation, remember rotation is the same thing as a revolution per second. To convert that into radians per second, I'd say 1 rotation is 2 pi radians, and now I've able to cross out my radians, and I've converted to radians per second. So in order to go from rotations per second into radians per second, you would simply need to multiply by 2 pi. Be careful in case I'm in minutes, because we never want to be in minutes. We always want to be in seconds. You'll need to convert that as well. Now, the second conversion that you need to be aware of is just like the first one. How do you convert actual tangential speed? And I'm going to start putting T's here for tangential, understanding that it's going around the circle. And your tangential speed, of course, as always, will be your angular speed times the radius. So you're going to start seeing this pattern that to convert back to actual distances, actual speeds, not angular speeds and angular distances, you simply have to multiply back in the radius. So let's do a real quick example. A wheel rotates at constant speed, revolving 6 times in exactly 2 seconds. Find the following. What is my angular displacement? So I've revolved 6 times. So my distance is 6 revolutions. And I know that 1 revolution is exactly 2 pi radians. And so I've traveled 12 pi rad. So what is then my angular velocity? Well, angular velocity is just displacement, angular displacement over time, which is 12 pi rad, divided by a time of 2 seconds. And I get, what, 6 pi radians? Now, you'll notice that a lot of times I will leave things in pi because it is easier to think about in that forms. So if it is rotated for 8.5 seconds, what is the total angular displacement? So using this equation but rearranging it, I can say my displacement is my speed times my time. Notice these are exactly the same as our old kinematic rules. So my speed is 6 pi rad per second. I want to use my units in here, times 8.5 seconds. Notice the seconds cancels, leaving me only with a radian, because that's a distance traveled. So I'm going to say 6 pi times 8.5. And again, I'm going to leave it in pi form. So it's going to give me 51 pi. So I want you to notice that if I wanted to figure out how many revolutions that was, because I want to draw it on here, I would recognize that 2 pi is 1 revolution. So this is going to go 25 revolutions plus another half revolution, because it doesn't go to 50, it goes to 51. So I'd go around the circle 25 times, and then on the 25th trip, I would go another half revolution. And so my finish would be right here. Hopefully this is a little bit reminding you of some earlier stuff from trig. So let's take a look at acceleration. Acceleration is equally as simple. Angular acceleration, which will be defined as alpha, lowercase alpha to be exact, is a change in angular speed or velocity over a change in time. So what would angular acceleration look like? Well, just to kind of give you an example, let's say I had a very small angular speed there, and over time, as this spot moves, I hope you kind of notice something, that my angular speed is increasing in the counterclockwise direction. So in this case, my angular acceleration is also counterclockwise. What is the units? Well, just like regular acceleration, units is going to be radians per second, or radians per second squared. Conversions, there's no real basis, no one ever says revolutions per second squared. That's kind of a strange thing, though you could. The only conversion we really need to know is if I wanted to know actual tangential acceleration, actual tangential values in meters per second squared, then I would simply take my angular acceleration and once again multiply by r. This is going to be an important case because you got to remember, anytime in circular motion, we also have centripetal acceleration, so we actually might have two accelerations simultaneously. Good news is one's pointed towards the center, one's pointed tangentially, and so they always form a right angle. So let's do an example real quick. A car accelerates using a 0.3 meter wheel to rotate from rest to 10 revolutions per second in exactly 10 seconds. Find the following. So notice the first thing is I want to convert revolutions per second into radians per second. So 10 revolutions per second needs to be converted into rads per second, and so I'm going to say 2 pi radians is equal to 1 revolution. My revolutions cancel, and that leaves me 20 pi radians. How would I find angular acceleration? Very simple. Angular acceleration is a change in angular velocity over a change in time. So 20 pi divided by a time of 10 seconds gives you 2 pi radians per second squared. Some of you may have said, hey, I'm, going through whatever. Now notice I did not use 0.3, but if I wanted to find my actual tangential acceleration, I would say, okay, that's angular acceleration times r. My angular acceleration is 2 pi times my actual radius of 0.3. And if I did that, because there's no real reason to use pi anymore, so 2 times pi times 0.3, and that would give me an actual acceleration of 1.9 meters per second squared. So that's kind of an extension of what I can do. So probably the trickiest thing with angular speeds is we deal with what's called a cross product. You've dealt with it before, and that was in electricity and magnetism, where you used your right-hand rules. So I want everyone to hold your gun out like you are with the FBI. I know the picture's a little bit different down here. Just imagine all 3 of those fingers being straight out instead of folded in. But you've got 3 different things you need to determine when trying to figure out what the sign is. There's a real quick shortcut, but I want to show you what's actually happening. So the sign of your actual angular equivalence is the direction of your thumb. Okay, the direction of W alpha or theta at any given moment in time is where you point your gun, and then your fingers always point towards the center of the circle. So here's what I want you to do. I want you to take a look at this first example. I want everyone to take a look at the right W. I want you to put your hand right over your sheet of paper. So if I'm off to the right, my 3 fingers should be pointed to the left. My gun should be pointed forward or away from me towards W, and you should notice then that your thumb is pointed straight up. Straight up is, of course, a period if we're doing 3D pictures, or out of the page, okay, is where your thumb is pointed. That is the positive z-axis. And notice, as you move to any 4 of these pictures and curl your hand around, if you point your fingers towards the center, if you point your gun in the direction of the angular speed and tangential speeds or accelerations, your thumb will always be pointed in the positive z direction or out of the page. And this is the reason that counterclockwise is positive. Not because we just arbitrarily picked it, but because when you do a cross product, when you cross these 2 guys together, you will end up with your thumb pointed out of the page. Now, in this example, I hope you notice that the speed is increasing, of course, over time, and so that should tell you the angular acceleration is in the same direction as the angular speed. And so my angular speed is also counterclockwise, which we now know that is, of course, a positive angular acceleration. Please remember, go all the way back to kinematics. When your velocity and acceleration are in the same direction, they're the same sign. Counterclockwise is positive. Clockwise, then, is negative. If you don't believe me, point your fingers the other way, turn your W around, and see where your thumb is pointed. It'll be pointed into the page, which is negative z, which is negative values. So I want you to give me a second, say pause me for 30 seconds, a minute, maybe even 2, and try these 4 questions. I want you to follow the directions, fill in each of the answers, and I'll give you a moment. So pause me now, try this page. All right, so hopefully you have paused me. Hopefully you've tried these 4 things. Let's go over them one at a time. So example number 1 says, and an object is initially spinning counterclockwise and speeding up. So W is this way, and because I'm speeding up, I know alpha is pushing in the same direction. So that means then that positive W and positive alpha. In number 2, the object is spinning counterclockwise and slowing down. So my angular speed or angular velocity is counterclockwise as stated, but because I'm slowing down, my angular acceleration is pointed the other way. Therefore, I have a positive W and a negative angular acceleration. Lastly, number 3, sorry. Object is initially spinning clockwise. That means W is going this way. It is speeding up, so alpha is helping him out. So that means I have a negative angular speed and velocity and a negative angular acceleration and velocity. So number 4, last one, object is initially spinning clockwise. So once again, angular velocity is clockwise, but I'm slowing down, so angular acceleration is opposed to that. So negative angular velocity, positive angular acceleration. Notice this is the only way we do signs. There's only positive and negative in here. You will have no vector additions. You don't have to worry about some type of 2D situation. Now notice that every other math scenario has worked, so it will continue to work here. We have a power 3 for my tangential equations or translational equations, and we now have a new power 3 for my angular equations. Notice it is a direct derivation. Velocity is now angular velocity, acceleration is now angular acceleration, and displacement is now angular displacement. Time is still time. Please recall, though, that this only ever works if your acceleration is constant. These should be memorized and known before you come to class next block. So let's do our last example and see what we can do. So let's imagine you're in a teacup ride. Ooh, isn't those things fun? So you begin turning the wheel at the center, causing the teacup to be angular. Let's see, teacup to accelerate angularly. It takes 12 seconds to fully rotate 3 times. So what is the angular displacement during the first 12 seconds? So I have 3 revolutions. I know 1 revolution is 2 pi, so my entire revolution or radians, my angular displacement is 6 pi radians. Again, if you want to try this before me, go ahead and pause it now and try it on your own. Part B. Part B, hopefully you've tried these on your own. So I know my initial position, I know my final position, I know the amount of time it takes. So we approach this just like we approached every other kinematics question. I have angular speed, initial and final. I have angular position, initial and final. I have acceleration, but now it's angular, and time. So I know the time is 12 seconds. I know my initial speed was 0. I know my initial position was 0. And I know my final position was 6 pi. So in order to answer this question, I look through my power 3 and say which one can solve for time, or sorry, solve for angular acceleration. So that is going to be angular displacement equals initial angular displacement plus angular speed times time plus 1/2 angular acceleration times time squared. So this is 6 pi, 0, 0, 1/2 alpha, and then it's 12 squared. So I multiply by 2, divide by 144, and your alpha is pi divided by 12 radians per second squared. So what is your final speed after 12 seconds? Well, angular equals angular initial plus alpha t. So final angular is initial angular plus pi over 12 times 12. My final speed is a pi radian per second. Fun little second question. At the halfway point of 6 seconds, how far have you angularly displaced? This goes back to my first equation that I used of my power 3. I didn't make you use the third one, such as life. Time plus 1/2 alpha t squared. Again, I'm now solving for theta, 0, 0. It's 1/2 an alpha of pi over 12 times the time of 6 squared. So I do 6 squared, that's 36. 36 divided by 12 is, let's see, 36 divided by 12 is 3. That's 3/2 pi radians. Which, by the way, if you notice, the first half of the trip, I only travel 1.5. I travel 4.5 the second half of the trip. So part E is meant to be a reminder. We'll get to this more a little bit in class because it's a little bit difficult, more difficult conversation, but I wanted to introduce to you today. So let's imagine that the 12 seconds have gone by and we're still accelerating, okay? But you've got to remember that we have an acceleration centripetal pointed towards the center, and we also now have a tangential acceleration accelerating around the circle. So that means in order to find my net acceleration, which would be somewhere like this, I need to use Pythagorean theorem and solve my question. So to do this, my angular acceleration, of course, was pi divided by 12. And I told you, didn't give you a good radius, but I wrote it over there, of 1.5. So I'm going to go ahead and just use numbers again now because it doesn't matter. So pi divided by 12 times 1.5. That gives me about 0.4 meters per second squared. Now, how do I find v squared over r? And I want you to notice this. This is actually kind of really important. There's an alternate form of angular centripetal acceleration. Velocity is wr squared over r. And when you simplify that, you get a very interesting alternate equation for centripetal acceleration, simply w squared r. So I know my w squared at 12 seconds. It was pi, so that's going to be pi squared times 1.5. So let's see what that acceleration is. Pi squared times 1.5. It's going to give me about 14.8 meters per second squared. And if you notice, this guy is dominating this one. And that's what you're going to find out. Over time, as you get faster and faster, this tangential acceleration is usually pretty small compared to the centripetal. Early on, though, sometimes it's worth. Because remember, this guy in this question is constant. This guy is increasing because you are speeding up. So if I wanted to do my total net acceleration, I would say the square root of 0.4 squared plus 14.8 squared. And let's see if it even makes it move. 0.4 squared plus 14.8 squared. Take the square root. And it goes up a little bit, not a ton. Let me make sure I did that right. 0.4 squared plus 14.8 squared. Oh, I put times in there. That would be the mistake. 0.4 squared time plus that. Square root the answer. And guess what? It's still 14.8. So we'll talk about sometimes we'll ignore the other component. All right, so real quick, just so you know, next block, finish your homework reflection, answer these questions. The first part you should have memorized. You should be able to repeat that. And you should be able to use your Power 3 to answer a simple question. I do also have on the homework page on the back some extra videos, some extra notes, and some practice problems and some conceptual building if you need any extra help. So take a look at those if you need to, but hopefully you come in prepared. Next block, we'll start with a little 10-minute discussion and then move on to a lab and some practice. All right, see you on, what's that, going to be Friday? Yep, see you on Friday.